Well, okay, it's really great to be here. Thanks a lot to the organizers well, setting this up and being and reorganizing this workshop. Try to see familiar faces and meet new faces too this week. So today I'm going to talk about well, sparsity in a deep context, and I borrowed some of this title from discussions with good old friend at the summer school, where good old friends coming from signal processing, having some complex with respect to deep networks, maybe, and wondering whether the depth leads to some sort of rupture, or whether we have a deeps complex. Okay, maybe the pen works in French, maybe less well in English, but anyway. Okay, so I'm going to try to do a survey of various questions on related to how the notion of sparsity can be adapted and maybe bring some surprises in the context of depth. So this is, of course, I need to thank a lot of people, and in particular, these colleagues, PhD students and postdocs with whom I've been working on various of the topics that I will be presenting. They really did all the hard work, and I'm merely giving a summary of what they did here. So some of you may be familiar with the notion of sparsity, and I will start with somehow the basic and the history of sparsity in the context of inverse problems and signal processing. So first, sparsity is really a principle for compression, frugality, economy of representation, with the idea that it's a natural objective to seek sparse representation where you don't want to spend a huge budget. But it's also something that has turned up to be a very useful knowledge, a very useful prior, something that you can exploit, or that you can promote in certain settings where, in particular, inverse problems where you have little information, little measurements. And the prime example is that of linear inverse problems. Although I'm sure that many of you are already familiar with it, I will spend a few minutes on linear inverse problems because they are a setting where we have developed some knowledge and some habits, and it's important to see how to remember these habits and to see how these habits can be slightly shifted when we go to deeper problems. So the case of linear inverse problems is recalled here. Y equals AX. Y is your measurement, is your observation. A is a matrix with more columns than rows. So there's fewer observations than the number of unknowns. It's underdetermined. But an essential achievement of the first decade of this millennium was the realization that under proper assumption on the matrix, proper sparsity assumption, this type of problem is well posed, and that algorithms with provable performance guarantees and provable tractability can perform the recovery in a stable manner. So, if you want to know more, well, there's the nice book of Simon Foucault and Holger Reuth. And now, so this has led to a real solid body of work in which much is understood in terms of interoperability, tractability, stability, etc. Now, to what extent can we use these tools beyond the case of linear inverse problems? So to begin, to give a taste of some of the issues that we can encounter when going a bit deeper, I would like to recall a simple example that we looked at with Alexis Benichou and Emmanuel Vincent a couple of years ago, was the problem of sparse blind deconvolution. So the goal is, you observe the convolution of two signals. You assume that the two signals are a signal and a filter. you assume that both of them are sparse, and you would like to perform the deconvolution, knowing only the convolved signal. So if you're not in a blind setting, if one of the two signals is known, let's say the filter is known and you want to recover the signal, you know it is sparse, it's probably a reasonable technique to use L1 minimization to perform recovery. And there are results to assumptions on the filter that will allow you to show that this works well. Vice versa, if you know the signal, you can probably recover the filter. But what if you try to do everything simultaneously? Well, a natural approach, something that would seem natural, would be to do this type of joint L1 minimization, minimize the sum of the L1 norms under the reconstruction guarantee. The reconstruction, well, while fitting your observation. And it turns out that this is something that will not work, that cannot work. The result is simple. It's if you're given the convolution of two signals and you try to address this optimization problem, well, the global optimum, well, there's a global optimum of this optimization problem, which is the Dirac on one side and, well, the convolution itself on the other side. And it's not a problem of the algorithm, it's really a problem of the cost function. And under the hood, what's going on here is there's an intrinsic scaling ambiguity in this deconvolution problem. So one, if you have a pair of signals that fits your observation, then scaling them in an arbitrary way, that doesn't change the fits. So when you think you're minimizing the sum of the L1 norms, you're actually minimizing the square root of the product of the L1 norms. And then it's not difficult to show that the product of the L1 norm of the filtered signal by the L1 norm of the Dirac is actually a minimizer. So what this can teach us is that as soon as you go slightly deeper than the linear inverse product, there are scaling ambiguities, and you should be aware of them. Maybe at some point we'll be able to harness them. But what is sure is that you need to be aware of them and take care when designing and trying to simply reuse our techniques in our L1 minimization techniques, for example. We should be careful. So if we want to go deeper, we'll go to deep networks soon, but something that is more familiar in signal processing is the notion of linear transform associated to fast transforms. And if you think of most of the fast transforms that you know, fast wavelet transform, fast Fourier transforms, they are fast because the corresponding linear transform, the matrix associated to the corresponding linear transform, can indeed be written as a product of a few sparse matrices. This is here, what I display is the matrix associated to the Hadamard transform. So it's a dense matrix of size n squared, and if you use it to store the linear transform or to apply this matrix to a vector, the cost is of the order n squared. But if you use its expression as a product of a few sparse factors, then the storage is decreased to n log n, and the cost of matrix vector multiplication is also decreased to n log n. So in this type of context, it's quite natural to try to learn or to approximate a given matrix as a product of sparse factors. And more generally, if you go to deep networks, so deep networks, there's the universal approximation theorem and much more that tell you how rich an architecture this is to express functions. But if you, so this expresses functions parameterized by weights on your network, but making the network sparse is potentially a way of reducing all sorts of costs to reduce the footprint of such networks. However, this requires finding efficient ways of identifying the location of the non-zero weights in this network, and also to learn these weights, to compute the weights. Today, the main way sparse networks are trained is by training a dense network and pruning it. So can we hope to do better? Well, I will not give an answer to this question, but hopefully some hints at special cases where it is possible to be more efficient than post-training pruning. Okay, so here is the journey I propose to follow together. We started by the linear case, which is well studied. We already had a first look at the bilinear case with this blind sparse deconvolution problem, but we'll spend some more time on the bilinear case before diving a bit further. So the bilinear case is interesting because it will serve as a toolbox for more for deeper linear problems under sparsity constraints. So let's look at this two-layer sparse matrix factorization problem. The problem is you're given a matrix A, and you're given two families of constraints, sigma left, sigma right, for the sparsity of your factors. For example, you may simply constrain X and Y, the factor that you seek to have no more than K non-zero entries each, but you can think of more structured constraints. And your goal is to find the best approximation of your matrix as a product of factors with these constraints. You may notice, by the way, that this is something, if under proper assumption on the support, this covers a number of existing frameworks, such as the LU factorization, or certain types of hierarchical matrices can be expressed in this under this type of constraints. And this is known to be NP-hard because it covers it covers a number of problems such as sparse PCA. But a question that we can wonder is what happens if instead of having a family of constraints, we actually fix the support. We know we fix the support, and we're simply looking to find the best approximation of a matrix by a pair of factors with a fixed support. One reason why this is interesting is that indeed, in the classical case of linear inverse problems where you solve y equals ax, you know that what is hard is to find the support. But once you have the support, there's a least squares problem. Finding the coefficients on the support is easy. And this also has led to algorithms that somehow can be interpreted as iterating between a search for the support and some kind of least squares regression to find the coefficient on the support. So understanding the fixed support case here is probably interesting. It will tell us something on whether it's feasible for this two-factor factorization problem, whether it's feasible to seek a support and update the coefficients in a tractable manner. So in particular, one could wonder, okay, if the support is known, can gradient descent method work? And if I have big matrices, maybe can I hope to have stochastic versions of this? Okay, I will not dig too much on stochastic versions here. So to address this question, well, in work with Elisa Riccietti and Kok-Tung Le, first question we investigated was the hardness, and it turns out that's not. I mean, that may come as a surprise if you think of if you thought of this problem as the equivalent of the least squares problem. But if you think of it as the equivalent, more related to sparse PCA, it may not be so surprising. So this problem, this factorization problem, is NP-hard. When the fact is essentially that well, as in any proof of NP hardness, you can reduce existing NP hard problem to this problem. And this reduction is from a matrix completion problem to a matrix factorization problem. Yes.
He said that if the supports were fixed, then it is easy. And now you're saying on this slide, if support's fixed, it's hard. Help me out here.
Thank you for interrupting me. By the way, I should insist that don't hesitate to interrupt during the session. So, what if the support is known? What I said is that it's easy for inverse problems. In the case where there's a single one factor is known, the other has a known support, but the coefficients are unknown.
Okay.
But it turns out that it's not easy when it's really two, three factors with fixed supports.
Thank you.
So indeed, so here the problem is you input an arbitrary, you input a matrix, you input the support constraint yj, and your problem is to find a pair of matrices xy. This is NP hard. This is essentially NP hard because there are hard instances of support constraints. So there will be also nice instances, support constraints, for which everything is easy. And you can think in particular, if you put no constraints, well, finding a factorization is not difficult if you have no support constraints. Yes.
The classical linear inverse problem, they are like it's NP hard unless you make assumptions of the design matrix. Without any assumptions, it seems natural to be super hard.
Absolutely. Unless I miss something, for the classical inverse problem, let's say when there's more unknowns than there's more equations than unknowns, and there's no sparsity assumption. That's not NP hard.
Okay, but the support is known.
I think here of the least squares problem.
No, the support is known.
Yeah. Now, of course, there's also this idea that if the support is unknown, it's NP hard if you have no assumption on the support, but if you have a sparsity assumption plus restricted isometric property, restricted eigenvalue property, etc., then things become easy. But here we're looking at the fixed support.
The reduction is by like a matrix completion.
It's a matrix completion problem. Matrix completion can be mapped to this type of factorization. And now, yes, it's NP hard, but there are easy instances. I already gave an easy instance if the supports are completely, if there's no constraints. That's a bit of a cheating. And so what the other thing we were able to demonstrate is that there are less trivial constraints, support constraints, for which the problem is completely tractable. And for certain support constraints, what you could show is that the problem is tractable with an efficient algorithm. And also that if you look at the landscape of the cost function, well, it has no spurious local minima and it has no spurious values. I can answer questions about spurious values if you're interested, but I propose to move on and maybe keep it as a subject of discussion later. Yeah.
The statement for any matrix A that it holds, the support INJ depends on the matrix A or not at all?
Thanks for the questions. Here is there exists support IJ. There's an identified family of support IJ for which we have these two properties. First, a given algorithm that works for all these supports provide the best solution for every matrix. And second, for any matrix, the landscape has no spurious object. Is it clear?
It's exactly my question. Thank you.
So it's yes, these are all supports for which everything is as nice as it could be. Now there are also, as I said, there are examples of matrices of supports where things are not that nice. And actually, there's one example which is a well-known one, where I have to admit, I wasn't aware of the difficulties related to the LU before investigating this problem. So the LU factorization problem corresponds to these two types of supports. I mean, the support is the blue part of the matrix. And if you go to a 2x2 case, you have a matrix Z. The whites indicate zeros, and you want to factor it as a product of two matrices with these supports. The fact that you want to factor it as a product of these two supports, I mean, you write it as XY, but you decompose in columns and rows. So it means that this matrix will be the sum of the product of these two vectors and the product of these two vectors. So it's the first is a rank 1 matrix with potentially all non-zero entries. The second is a rank 1 matrix with only one non-zero entry. But now, if you observe, well, the first, the upper left corner, there's a 0 here, and it's the sum of a 0 here and an entry in this matrix. So this entry has to be 0. This is a rank 1 matrix. So this is the product of these two entries. Being the product of these two entries, at least one of these has to be 0. Let's say, for example, the top one. So the whole row, the whole column is 0. And now, since this is 0, it means that you should have a 0 here. So this is a matrix that cannot be written exactly, that doesn't admit an exact LU decomposition. And yet it is known that every matrix can be approximated arbitrarily well by an LU factorization. Yes.
With pivoting, can you permute the order of the columns and rows, and then it becomes possible? Just to understand, make sure.
Yes, this is known. When you allow pivoting, things become fun. But here, this is with fixed support.
This is just to make sure.
But you're right. It's good to put the dots where they need to be. So this is by the way an example where illustrating that the problem, this sparse matrix factorization problem is not even closed, and there's no minimizer to the cost function. And in fact, it turns out that related settings that are not DLU can be found in practice when trying to do deep factorization of, and that can lead to divergence of algorithm, because to get an arbitrarily good approximation, you need to have one factor that diverges to infinity, at least. So now let's look at the concrete cases where things behave nicely. I could go back one. If you have just a full support, it's easy. It's essentially let's say you have fewer columns on the X matrix than the ambient dimension. So you're simply looking at low rank approximation. Use your favorite SVD to compute a solution and truncate it. Now, to go further, essentially, what we do is again the same decomposition as I showed for the LU. You write your matrix product as a sum of rank 1 components. And initially, what you have is support constraints on the factors X and Y. Now you translate them into support constraints on the rank 1 components. And it turns out that if these support constraints are disjoint, well, things are easy. You simply take your initial matrix, decompose into blocks, do best rank 1 approximation, and you're fine. Actually, if they're disjoint or equal, pairwise disjoint or pairwise equal, then you can do a higher rank approximation and everything works well. And under a slightly weaker assumption, we can deal with partial recovery settings where there's partial recovery of certain supports. And this leads to an algorithm which is essentially like the SVD, a greedy algorithm that selects the support in the right order and performs low rank approximation and finds the optimal solution. Here is an illustration of how this algorithm behaves on some examples. And it's compared to what you would probably do naturally in this setting, which is gradient descent on your pair of factors. So either plain gradient descent or with momentum or with Adam. So on the horizontal axis, you see the runtime. On the vertical axis, you see the precision that you reach. And so all these are depending on the number of iterations for the iterative algorithms. But for the proposed algorithm, it's just essentially in one shot that you get the machine precision. Yes.
Does not find the global optimum?
How come does Adam does not find the global optimum? Honestly, I have no answer here. Actually, here we were quite surprised that to see that gradient descent performed better, but essentially, I would ask you if I had to know more. I don't think there's anything that tells you that Adam is supposed to be always better than.
More or less, if you set some parameters, Adam includes gradient descent if you set the parameters correctly.
If you fix the parameters.
If you take Adam as being Adam with the default parameters, I can imagine. But if you start to play around with step sizes, it includes more or less gradient descent.
Sure. So I'm assuming this means that there was no tuning, absolute tuning of the parameters to find the best tuning of Adam for this problem. We have done more. There's an updated version of this figure in preprint that we released, and where Trump did all the work of tuning the parameters for each algorithm and still getting like the 10 or well 2 orders of magnitude faster methods.
Just to understand better, can you summarize again what the algorithm is that's doing so much better?
So this algorithm is an algorithm that takes the input matrix, takes the prescribed supports, transforms these supports in supports of rank 1 constraints, and extracts the corresponding blocks of the input matrix, does low rank approximation, and maps everything back to X and Y.
It's very much dependent upon the presumed constraints on.
Yeah, so this is an algorithm that cannot work for arbitrary supports I and J. It will work for supports that have that satisfy the assumptions of the theorem 2. For such support, it's an algorithm that gives a machine that provides a solution with machine precision in a controlled complexity.
You're not assuming that A is exactly one of these, right? You're just asking for the XY decomposition that's closest to it that satisfies these constraints.
So what I'm assuming is that I and J, the discrete support patterns, satisfy certain conditions.
Yes.
Exactly. And now I can take any matrix. I mean, it can be a matrix that has an exact factorization, can be a matrix that doesn't have an exact factorization. The algorithm will provide to machine precision the best factorization of the thing.
But your error here is really tiny. So the A you were
here I used as an input for this numerical. I use the matrix that is that satisfies exactly that.
Thank you.
Yes. Otherwise, the difference would not be that visible. That's mainly the reason. Thanks for the occasion to clarify. Okay, so that was about the bilinear case, where we already had this surprise that, well, something that looked like the least squares problem is not as easy as the least squares problem, but can lead to, under some assumption on the support, to something tractable. And now let's look at how it can be used in deeper context. Here, we focus on the problem of factorizing a matrix as a product of sparse factors, but we'll assume some structure on the supports of these sparse factors. And the structure that we'll assume is the so-called butterfly structure. I will spare you the details of the butterfly structure, but it's illustrated here. You see it's very structured sparsity patterns. There's at most 2 non-zero entries per row and 2 non-zero entries per column of each factor. And there's even much more structure than that. This is a common structure to many fast transforms, such as in particular the Hadamard and the Fourier transform. DCTs and the discrete sine transform, the discrete cosine transform are also closely related. So it's so this is a type of structure. Well, it turns out that well, you could again try to use Adam gradient descents with your fixed support to try to optimize the coefficients. But an alternative is to use a hierarchical approach. We're revisiting actually an approach that was developed in the PhD thesis of Luc Lemagouarou a couple of years ago. The idea is that because of the particular structure of the factors, you can, if your matrix is the product here, it's exact. I'm assuming that the matrix is exactly the product of such sparse factors. So you can write it as a product of the leftmost factor and one factor that's the result of the product of all the remaining factors. Well, it turns out that this product of remaining factors still has a constrained support, and we know the resulting support. So what we can do is start from our matrix and solve a 2-factor problem using the algorithm that I've just described, because these support constraints exactly satisfy all the assumptions we need. And we can repeat the process until we reach the desired factorization, because we can prove that with the butterfly supports, all the assumptions of theorem of the previous theorem are always satisfied. So if you start from a matrix that has an exact factorization with the butterfly supports, then you will retrieve factorization with I mean, you will retrieve an exact factorization. Yes.
It's a bit hiding under the carpet all the condition and those support. What does it mean actually? Because here you say, okay, if the conditions are satisfied, then this algorithm is going to work. But what are exactly those conditions of the support INJ?
First, a cheating way of answering you is there in the paper. Now, a slightly more precise is essentially this idea of having disjoints. You take your support, you map them to rank 1 support, and now the rank 1 supports they're pairwise either disjoint or equal. So and in fact here everything is disjoint. So you can really take your supports and map them to a partition of your matrix, and on each block, I mean they're not contiguous blocks, but on each block you can do a best rank 1 approximation and all that. Does it answer your question? So here I would not even need to invoke theorem 2. That was also written in a way, I mean, in a more abstract way, but because we have slightly more relaxed conditions that still allow the algorithm to perform. So here, what I did. Yes.
I have another question. So here there is kind of ordering in this algorithm, right? If you start with the step 1, but what if like you start with another step? Is there something happening?
You cannot really start on another step, but I think I see what you mean, because this is precisely something we studied. I mean, look at the top. You can either try to isolate one factor and consider the rest as a product, or you could start from the left, isolate this factor and consider the rest, or you could actually use any binary tree. Works with any binary tree. You can use any binary tree. It will in all cases, the hierarchical approach will work and will provide an exact factorization if you start from a matrix that has an exact factorization. And we also studied the complexity. If you use a full SVD and then truncate it, it's better to use an unbalanced tree to do it either from the left or from the right. And if you use the balanced, if you want to use the balanced tree, it can pay off if you use a specific algorithm that directly do truncated SVD.
Maybe my questions help. I don't know, but if you go back, if we have the DFT, not only are the factors of the specific patterns, but have specific values there. So what you're doing here is it's like doing a DFT, but you're finding the coefficients that go in these patterns,
yes,
instead of presuming the DFT coefficients. Am I understanding?
So yes, the DFT matrix can be written as a product with this support pattern.
Yes.
And the coefficients are complex exponentials with very particular
value.
But what we're doing is something that, I mean, you can take as input the DFT matrix and we recover the complex exponential up to some scaling because they are natural scaling ambiguities. But that's, I mean, we're happy if we recover everything up to scaling. But this allows also to recover as efficient factorization, even if your matrix is not the DFT, but another matrix that has this type of factorization.
Yes, and somehow it should be at least as good as if you had used, a DFT, because you have more freedom.
Yeah, it gives more freedom. It depends on your context of application. But for example, if you want to do a non-uniform Fourier transform, there are techniques for non-uniform Fourier transform where you use this type of approximation where typically the coefficients are tuned analytically. Here you can tune them numerically with still something. This gives me another opportunity to insist that here these exact recovery guarantees and so on, they are valid when you start from a matrix that has an exact decomposition. When it doesn't, numerically things work well. It seems reasonable that an analysis of stability can be conducted, but here then it's there's less to be said. Okay, so another way of completing my response is if you start from a matrix that can be written as a product of logn factors, well, the naive matrix vector multiplication costs n squared. But if you use the factorization, and if you have an efficient implementation of sparse of the corresponding sparse matrix vector algebra, you get an n log n multiplication. It's also n log n in storage. Now, if you know that it's with the butterfly supports that this factorization occurs, then starting from your matrix that costs n squared storage, you can retrieve the factor with an algorithm, and the cost of the algorithm is O of n squared. So essentially, if you know that you're going to apply this matrix a number of times, then the overhead of computing the factorization beforehand is not huge. And then you get in the n log n regime rather than the n squared regime. And okay, here, I mean, there's something called lottery ticket hypothesis in deep learning that says that essentially when you train deep networks, there's often a subset of coefficients that you can select after training, but if you once you know them, you can train and get the same error. This somehow says that for if you get to to sparse supports that have this butterfly structure, you don't even need to retrain. You can, and if you're in a linear setting, so I'm making very essentially analogies, but here you have a setting where there's a way to directly compute the coefficients of your sparse factors without the need to do gradient descent type methods. Yes.
Algorithm stable under perturbation. Assume you have a matrix whose exact version has this factorization, but now you impose a slight perturbation.
So we haven't formally analyzed it, but it's based on decomposition. I mean, and with two factors, it's based on decomposition into blocks and SVDs. So essentially, it should be reasonably stable. But I don't. Okay, I prefer to discuss it offline. We have observed numerically also that you had noise. Things degrade smoothly.
Mm-hmm. Okay. So you have empiric stability.
Yes. Okay, and everything has been implemented in a software library that can be installed either on Python or MATLAB. If you have a matrix, essentially you write a butterfly of A and you get a butterfly factorization that you can use then in your algorithm. If you have an orthogonal matching pursuit with a matrix, well, use it with orthogonal matching pursuit with the factorized version, and you benefit from the acceleration. I should be soon to complete soon, right?
5 minutes, yeah.
Okay. So it will be just enough to touch the surface of something where we start to introduce nonlinearities. So just a bit. So we'll be working here with ReLU neural networks. I've decided to plot them from bottom to top, the input, the output. You probably know the terminology, so I will not spoil my 5 minutes discussing it. And so okay, there are a number of so the parameters are the weights of the hidden linear layers, and it implements a function called a realization. When a property that is important is when you use the ReLU as the nonlinearity in this network, is that this is a positively homogeneous function, which implies that there is again some scaling ambiguity or some scaling invariance in the parameterization of these networks. So if I just zoom on one particular neuron in the network with incoming weights and outgoing weights, well, if I simply, if the only thing I change in the network are these incoming and outgoing weights that are multiplied here by some scalar, positive scalar in here, divided by the same scalar, then the function that is implemented by the network doesn't change. This is reminiscent of a thing we've seen in the linear case, and indeed, that's also visible in a nonlinear case. So this gives rise to equivalence classes of parameters. You can define an equivalence relation with respect to this positive rescaling operation. This positive rescaling operation implies functional equivalence. That's the functions that are implemented are the same. So this gives some level of freedom. If you have a parameter, you can play with this parameter to try to change the behavior of certain things you do with networks. Things you do can be training the network or can be quantizing the network that will not be invariant to scaling, but the functions are invariant to scaling. So it's for example, it's possible to use this during SGD optimization because, well, I'll illustrate it in a minute, or during quantization to try to exploit this invariance. So, for example, a typical operation for training a network would be a succession of SGD steps, so stochastic gradient descent. But what you can do is between two steps to insert something that will play around in this scaling equivalence class. So, and it turns out that the gradient that you compute is not the same if you compute it at two different scaling equivalent parameters. So in a paper with my former PhD student, Pierre Stock, what we propose is a method to choose. It was essentially really a heuristic among the vectors in this equivalent, the parameters in this equivalence class, choose one that minimizes some cost. And here the cost was an LP norm. it turns out that because of this, scaling equivalence, it's really for NEP, this can be expressed in fact as a convex optimization problem. There's a unique global optimum, and you can compute with a synchron-like algorithm. So this is something we tested numerically, and it turns out that it can combine with standard techniques, standard tricks such as batch normalization. It can provide improvements, in certain settings. As always, in deep learning, I mean, you can select training sets where things are and problems for which there's an improvement. It's not universal. The other thing that you can do, and we didn't do it, but that's this was picked up by some colleagues, is after training, use this rescaling technique to find a parameter that is equivalent but is better balanced, so that quantization behaves better, and after post-training quantization behaves better. So these are illustrations of the fact that in some cases scaling equivalence can be a blessing, and I mean you can try to harness it. And 2 minutes, 0 minutes. So maybe the last thing I want to mention is that because there's this scaling equivalence, but it's not always convenient to work with parameterization, which is not intrinsic. I mean, there's really a difference between the parameters and the realization. So, in particular that if you have scaling equivalent parameters, they lead to the same realization. It would be convenient if this was actually the character. I mean, if functional equivalence was the same as scaling equivalence, plus permutations, because there are permutations of neurons, of course. But that's not. At first, that's not always the case. There are exceptions that we exhibited, and it's also but in the process of trying to better understand what is the relation between these two, this notion of scaling equivalence and this notion of functional equivalence, we came up with a sort of embedding of parameters that really captures the scaling equivalence and is a representation that is not yet something convenient and tractable to work with, but at least mathematically, it's a representation that we found out to be useful to capture concretely the scaling equivalence. So if you have scaling equivalent parameters, they have the same embedding and the same signs. And this is almost always the case, except for very degenerate case called non-admissible parameters. Having the same embedding also means that you have the same realization. And the converse was also analyzed, but only on at a local scale. And going beyond the local scale is still a bit technical, but involves the analysis involves an analogy with linear inverse problem, because somehow this captures the locally linear behavior of the networks with respect to their parameters. Okay, I think I'm out of time. I mean, I can give some to those who are interested some details on how the embedding is constructed. Here, I just gave an abstract description. It's not very complicated, but I'll skip it. And if you have a few things to remember from this talk, I think I would like to emphasize the fact that what you know about sparsity in linear inverse problems doesn't necessarily hold as soon as you add layers. So we got some surprises in terms of problems that don't have a minimizer, problems that we thought were easily squared and become NP hard, but yet the methodology of restricting the problem, identifying the well-posed cases seems to still offer some promises. in the course, we encountered some optimization problems where we could actually get rid of gradient descent using rather some kind of spectral techniques. SVD is reusing SVDs, and so something I believe is quite intriguing and promising is to understand to what extent we can harness the scaling invariance in deep ReLU networks to, for better training of sparse networks. Thank you for your attention.